Optimization. So those of you who've taken an optimizations class, the first part is going to be very basic for you. Okay? Basic enough that if you have something better to do or grab a coffee or whatever else, go ahead, do that. Yeah, save yourself some time. Okay. So just to set the context a little bit. But we're actually going to look at scalable things, and I mean, you might be surprised, but occasionally people still publish essentially the same algorithms of what I'm telling you now as new stuff. So let's look at some of the things that we're going to do. We'll talk about simple things like gradient descent, Newton method, conjugate gradient, and then BFGS. Everyone would have probably played with BFGS at some point. Then we'll talk a bit about constraint optimization, just Lagrange function, Wolf dual, and all that. That's probably as far as we're going to get today. Then distributed subgradient methods, bundle methods. So these are a few optimization techniques. Some of them you might have seen, some of them you might not have. And then we'll talk a fair amount about online optimization. And in the end, essentially a set of other useful optimization techniques, mainly for discrete optimization, randomized methods, that you might find useful if you have to solve optimization problems of this form. So why do we care about optimization? Let me give you a little bit of context. So what we saw last week when we looked at exponential families, we basically had maximum a posteriori this type of optimization problem. And those of you who've done the homework would probably recognize some equations ever so slightly. It's not quite the same equation, but some solution might look comparable to what you might see here. So basically the negative log posterior, is given by some negative log prior, throwing away the constants here. And then here is what we get from our exponential families expression. Of partition function minus this linear form. Now if we have a lot of data, and this is one of the problems, it may not fit into a single machine, we might have bandwidth constraints, and our amount of data might actually grow in real time. Now there's another source of such optimization problems called regularized risk minimization, and we're going to talk a bit more about that in a different context. So quite interestingly, both the Bayesian approach and the frequentist approach will give us related estimation problems. Now, a true hardcore Bayesian would be very upset and cross with me for arguing that you should maximize this. Well, why is that so? Because the negative log posterior need not necessarily be very correlated with the posterior distribution of a parameter. Let me give you an example where this is a horrible approximation. Well, let me first give you an example of where this is a good approximation. If this is my posterior, then maximizing this is going to be pretty good. And in many cases, you can actually show that you get concentration of measure around that mode. And many log concave posteriors are going to have that property. However, a lot of interesting estimation problems don't have this property, but they may actually have a lot of modes. And you can immediately see that if I put another mode here, maybe not quite as high, then the maximum posterior estimate, which maximizes the posterior, so P of theta given the data, is going to be horribly different from, this is theta of course, this is going to be somewhere close to the expected value of theta. So in expectation, theta is going to be very, I can make it arbitrarily bad relative to the mode. So be careful when you deal with those problems, because they need not always give you very meaningful answers in a Bayesian context. In some cases they will, and especially when you have a convex problem, convex optimization problem that you get out of that, things are going to be usually very good. Yes. Okay, so the posterior distribution, if it's, let's say, bimodal, let's say this is, just, let's say the weight of somebody. Then the expected weight, let's say this is maybe, I don't know, 50 kilo and that's 80 kilo, right? Then the expected weight is going to be, somewhere in between, maybe around, 65, 70 kilo, whereas the mode, maybe there are, more heavy people than light people, is going to be, 80 kilos. So you're going to be really badly off in terms of finding the mode of the weight as opposed to the expected weight. And you can construct cases where this is arbitrarily nasty. Example would be if I add some, permutation symmetry to a problem. Then the expectation that actually is going to go away. Yep.
Could you relate that mode versus mean idea to the equation again?
Okay. So this equation is a nice one. This is one where the rate case happens. We have a single mode. And we're actually going to prove that we have a single mode. And you can see that because this function is convex. It's basically, parabola, glorified parabola in many dimensions. This is a convex function. And this is a linear function. It's going to have a single mode. So of course, even for that, the mode and the mean may differ, but they will typically not be too far off. And in some cases, you can actually prove concentration of those two. So which, in other words, tells you that, yes, I run the optimization problem, I get the solution that's maybe not quite ideal from a Bayesian point of view, but it's not going to be so horrible. And that would be a little bit beyond the scope of this class, but there are cases in which you can prove stuff like that. In general, however, well, this is the case that you need to worry about. Sampling can actually work around that. Sampling can work around that, and we will discuss a lot of sampling towards the end of this class. Also, in some cases, variational methods can work around this, where you might have several modes of the distribution. Okay. Now, an interesting distinction that quite often occurs is batch versus online. Now, this is more a practical thing than a conceptual one. In batch settings, we basically typically have a very large data set available, which we received in whatever way, and we want to get some reasonable parameter. So, for instance, I might have a large annotated corpus with, speech and annotation, and I want to build a good speech recognition system from that. Or I have, scanned in books and the corresponding text, and I might want to build an OCR system based on that. Or image annotation, categorization, and so on. So whenever I have a lot of log data, a lot of log files that I want to use, batch tends to be at least an important component of our problem. Now the other part is online. So that happens quite often where I have a real-time data stream coming in, and I need to respond in real time, update my parameters in real time. For instance, computational advertising, it's a good idea to know very quickly which ads are popular. Because if I know which ads are popular, I'm going to show you a lot more of them. Likewise, content recommendation, collaborative filtering. So if I know that a news article is very popular, I will show it a lot more. If it's a dud, I will not show it because nobody will click on it. Now, reality is usually somewhere in between. Because in reality, you will have, a big database of log files, which has more of a batch-like nature. And then I will have, on top of that, a real-time system running, which requires me to respond and update in real time. And that actually makes for very interesting algorithms, which I think haven't been published as much as they should have. So the problem is also you have a lot of parameters. You might have like 100 million to maybe 1 billion parameters. So for instance, if I want to do personalized content provision, it's really impossible to adjust all those parameters heuristically or manually. So this is why I really need to optimize. You would be surprised how many people in information retrieval still tell me, yeah, okay, well, give me these parameters and I'm going to compute the cosine similarity score and everything's going to be good. No, it won't, because the cosine similarity score is something completely made up and you have no way of telling whether it's actually going to be accurate. Might correlate reasonably well in some cases, but overall you really want to optimize things. So don't just use that cosine similarity score. If you learn nothing else from this class, it's already good. The other thing is, well, you know, one of the interesting challenges, I might have, you know, 1,000 to 10,000 computers which are running my advertising system. Now in that case, well, I can't really possibly go and exchange all the data between all the machines in real time. I can do that occasionally in the back end periodically. So I need to actually deal with distributed optimization. I need to deal with multi-core machines. So if you just look at the number of cores per machine plotted over time, you will see a nice, you know, factor of 2 increase every couple of years. What this means is that essentially processor cores are not really getting much faster anymore, a little bit, but not much, but you're getting more of them. And at the moment, you're still in a regime where you can get away with writing codes for single core. After all, this machine has 2 cores. Probably the more recent laptops that you might have 4 cores, and maybe they have 4 cores and 2 threads for each core, so they might have, you know, like 8 fake cores. And you can still get away with writing single-threaded code, right? You only pay a factor of 4 maybe. In maybe 5-6 years, that's going to be a really bad idea. So you want to design your algorithms to, you know, work for multi-core, multi-threaded settings right away, right now. Because you will need them in a couple of years. Okay, so let's look at unconstrained problems. And who doesn't know what a convex function is? Okay, no hand should go up. Thanks. Thanks for being brave. Thank you. So, okay, so here is a convex function, is a convex set, and of course we do set. So basically, a convex set, in the simplest of all terms, is, well, you know, I take one of those sets and I can put the line into this set. At any point, if the 2 endpoints are in the set, the entire line is. So what I just showed you with marker, well, you didn't see it. So that's what a convex set is. I can basically take linear combinations and I stay inside. Now a convex function is one where I can take a linear interpolation between the function values, and of course there's one lambda too many, and but it's okay for the rest. Then, you know, this upper bounds the function. In other words, something like so. That's a convex function. So this is a very, very simple definition, but it's extremely powerful. So the first thing that you can immediately see is that the below set of a convex function is convex. Okay, how are we going to see that? Well, you know, we pick some threshold, let's say C, and we pick 2 points within that set. Then, well, let's just prove it. So I pick all points with the property that f of x is less equal than some constants. I define the set to be C. Now, if I have x and x prime in C, then I know that for both of those, this is satisfied. Now, I also know that for any point on the line, so f of lambda x plus 1 minus lambda x prime, by convexity of f, this is less equal than lambda f of x plus 1 minus lambda f of x prime. Now this is less equal than C. This here is less equal than C. So this is less equal than C. I've just shown that the below set, so the level set of a function, of a convex function, convex set. This is not the only way how I can construct convex sets. For instance, I could have just applied any monotonic transformation to F, which might very well have broken convexity, and I still get convex sets as below sets. But we're not going to worry about that here. The interesting thing is that convex functions don't have local minima. And we can immediately see that. See, here's our function. Here's one local minimum, here's a local minimum. If it's a self-respecting convex function, then I could, draw that line in between. That would be an upper bound, which is a contradiction. That's why this cannot happen. Okay. A few interesting properties. So the vertices of a convex set. These are basically the ones where I can't really extrapolate further. So, in other words, if I pick one of those vertices, then for any point within any other point within the convex set, where I draw a line from the vertex to that point, if I want to go beyond that point, I will leave the set. So this has interesting consequences. Let's say, for instance, I take, the circle. Then the set of vertices is the entire boundary here. Why? Because, well, any point on the boundary here, as soon as I draw the line through it, it will exit from the circle. So this is just to keep in mind that the set of vertices need not be finite, need not even be countable. Convex hulls? Well, I just take linear combinations with, weights some, bounded by 1, and the convex hull of the set is a convex set, and that's straightforward to show. Now, this is an interesting one, and it can be sometimes quite useful. As a matter of fact, we're going to use that for linear optimization problems, and especially total union modularity in a moment. So the supremum on a convex set, on a convex hull, so the supremum of convex function is, on the convex hull, is on the vertices. So that proof is very simple by contradiction. Let's take the maximum of the convex function on the convex. Okay. So the maximum of a convex function on a convex set is obtained on a vertex. So let's assume that it were somewhere inside. We're just going to prove it by contradiction. Then, well, this cannot be the maximum because we can do this upper bounding, right? So that's our convex set. We want to maximize some function on that set, and that function is convex. So let's say we pick some point in here, and we claim that this is the maximum. Then I can pick two other points to form a line with. Now by convexity, this point here in the middle cannot be the maximum. Because if that were the case, we would get something like this.
You mean strictly convex?
What?
You mean it cannot be a strictly convex?
So so you're one step ahead of me already. So the thing is, I didn't say that I can find a vertex only on the vertex, the maximum only on the vertex. So if I have just a convex function, it's very well possible that there exist some points on the inside that also attain this maximum value. If I have a strictly convex function, I know it can only be at one of the vertices. In the other case, for instance, I could have an entire edge here. That's, maximum. So for instance, if I have a linear program and my objective function vector is normal to that edge, then all values here on that edge are going to be the same. And then all of those are going to be equivalent solutions for that maximization problem. In some cases, maximizing convex function over a convex set is actually an interesting problem that is very cheap. And in that case, it's good to remember what the vertices of the set are. In some cases, it's hideously expensive. So for instance, take a quadratic function, right? Sounds nice, you know, convex quadratic function, and I have box constraints. In other words, all the values for the coordinates are between 0 and 1. Then in d dimensions, I have 2 to the d vertices. And I pretty much have to evaluate the function on all 2 to the d vertices to find out where the maximum is. Well, I mean, I can do some branch and bound and all that, but essentially, it's a hard problem. Yep.
Well, based on the previous slide, you said that like convex functions can't have local minima, right? Is that concave functions you meant?
Well, convex functions cannot have local minima.
But you just said x squared is convex and x squared is local minima.
I don't understand. X, how can x squared be? So what I can have.
Oh, I know what you mean by that.
Okay, so here's what you can have.
You mean local minima excluding global minima.
Okay, so, well, okay, so you can have this case, right? This is like a bucket. So the bucket is a convex function. And the bucket has a flat bottom, which is, you know, the global minimum. However, it can have many minimizers. Any point on the surface of the, on the bottom of the bucket is a minimizer. So you need to be careful in distinguishing. By the way, thanks for bringing this up, because it's an important distinction. There's a difference between the minimum value and the minimizer. The minimizer need not be unique, but the minimum value is. Big difference. And in some cases, you just want to have a point that has the minimum value. Now, an interesting thing is the set of all minimizers is a convex set. That follows immediately from the fact that the below set of a function, you know, for any threshold is convex. More specifically, that's also the case for its minimum value. You have a question?
The definition, the first definition.
Yes?
X prime not X.
Yep. So basically, so what I'm doing is I'm picking 2 points in my convex set. And what I'm doing is I'm saying, well, I take the line segment between x and x prime, and I extrapolate it beyond x prime. Sorry, I extrapolate it beyond x.
It should be for all X prime not X.
Well, no, x prime is in x is in x, but the extrapolation leaves x.
Are you sure the number is greater than 1?
Yes.
Oh, great.
Yes, it has to be great. So basically, I'm piercing that set. Well, let's take a simple case. Okay. Well, let's pick this point here. This is a vertex. Now, any other point here, that line segment is still in the set. Now, for lambda greater than 1, I exit my convex set here. I pierce it. It doesn't really matter which point I pick. It's always going to point outside. Right? If I pick my line segment somewhere here, it's not going to point outside. That's the trick.
I didn't see the line.
Yeah, sorry. Okay, so this is sometimes just quite useful. Okay, now let's do something very, very simple, gradient descent. So for that, we're first actually going to have to do something even simpler, namely just, you know, one-dimensional line search or interval bisection. And if I have a convex function, finding the minimum for a one-dimensional problem is trivial. I start with, you know, 2 boundary points. Let's say those 2 guys here. I pick the one in the middle, and I look at its 3 values. Okay, fine. So now, what I can do is I can check whether, you know, the minimum is going to be here on the left or the right. How do I check that? I look at the first derivative at point 3. If I don't have differentiable functions, then basically I need an extra 2 points. You can think about how you get that. But if it's differentiable, all I need to do is I just check which way the gradient goes. The gradient points to the right, I keep on moving here. So I look there, points me to the left, and I keep on halving the interval. So therefore, after k steps, I am left with 2 to the minus k times the original interval. So this is a very simple algorithm. You can do a little bit more clever things and look at maybe what the value of that gradient is. You might not have exactly in the middle. If you don't have differentiability, you have to evaluate function values at some points, and you might get the golden ratio and so on. There are lots of other variants which can make the algorithm ever so slightly faster. For the idiot-proof simple version, just use this. It's good enough. Now, this is going to be a useful subroutine for a very powerful optimization algorithm, gradient descent with line search. And this actually is nicely convergent. This is, if you have a simple differentiable convex function, this may very well be all that you need. So the idea is that the gradient actually points into the same direction, and locally this gradient is very good. Now, what we therefore do is we take the gradient direction, we perform a line search. Now it's a one-dimensional optimization problem. That's straightforward. And okay, well, we still have the issue. We don't have the right inside boundary, but you can figure something out by just exponentially doubling intervals if you realize the minimum isn't there. But anyway, and then at that new point, you basically perform a new line search, compute a new gradient, perform a new line search, and you keep on iterating. So it's about as simple as you can design an algorithm. And it actually has very nice convergence guarantees. They're basically, the Newton method has better ones, but other than that, this is pretty good. So let's suppose we have what's called a strongly convex function. So strongly convex functions are kind of nice. It means basically they are more curved than parabolas of a certain degree. So usually for a convex function, what you have is So usually for a convex function, you can compute the tangent, and you know that all other function values are above. Right? That's what a convex function does. That's the corollary out of the fact that any linear interpolation is above. So any Taylor expansion of first order is below. Now, what you sometimes may be interested in is by how much this function here deviates from my interpolation. And strongly convex functions are guaranteed to diverge from that by, I can basically draw another parabola, which gives me a lower bound of the amount of deviation from that tangent. I don't know whether that now looks very much like a parabola, but that's the general idea. I can sandwich a quadratic function in between my lower tangent and the actual function. Now, in many cases, we are also going to use the fact that these functions have a bounded Hessian. So in that case, I can upper bound things by another parabola. So what this means is that it's really only that region here where I need to look for solutions. And that's what makes algorithms converge rapidly. Who has heard of the condition number? Okay, a lot of hands go up. Good. So condition number, remember, in linear algebra was the ratio between the largest and the smallest eigenvalue of a matrix. Now this is essentially the equivalent of this condition number. So the condition number explains how difficult certain linear algebra operations were. Here it's the ratio between that lower parabola and that upper parabola of those two curvatures that tells me how hard it's going to be to find the minimizer. And as a matter of fact, specifically if I have a quadratic objective, the condition number is going to be that ratio. So it's a strict generalization of that. So if I have a strongly convex function, I have this lower bound, which is good because it gives me certain guarantees on the progress guarantee. So I know that if f of x minus f of x star, well, if this is the case, I can just go and actually minimize, right? And I get that this is m over 2 x minus x star squared. So all I need to do in order to get that inequality is just, pick y equals x, and x equals x star. And then, of course, the gradient here vanishes. So this is 0. And we have exactly that. Now, I can also get a lower bound on the minimum. And all I do is I just use that same inequality again, and I just expand at the point where we currently are. I just swap x and x star in their rows. And I get this upper bound. So in other words, the size of the gradient tells me how far away from optimality I'm at most. So this tells me that in terms of function values, I'm not much further away than how far the points are to each other. And this tells me that the function value, the difference in function values is bounded by that gradient.
Explain the last equality.
Okay, so basically we just use this inequality here twice.
No, I mean the last slide.
Yeah.
You want the C minus something equal to 1 over 2m.
Okay,
Good. I don't see.
okay, so what I then do is I just perform an optimization of a y.
Quadratic form.
Yeah, this is a quadratic function. For x fixed, I can just, maximize that with, minimize that with respect to y. And then I get this expression here. So that's basically what you do. Now, furthermore, to get the upper bound, this is exactly this top curve here. So if I assume that I have a bounded Hessian, I can therefore also guarantee that, my progress can't be too bad. So that's this thing here. So in other words, if I know that f of y is less equal than f of x, plus that linear extrapolation, plus that quadratic term, that's the upper bound on the Hessian. So therefore, especially in the line search direction where, y is t times, the gradient at the location x, right? So we have f of x. Now we plug in y minus x, that's just, t times the gradient, times, well, that's already the gradient itself, so it's t times the norm of the gradient squared, plus m over 2 t squared norm of the gradient squared.
So here gx is the same as partial x angle x.
Yeah. Yes. Yeah, that's the slide here. Perfect. And then, you just minimize that and you get this. So therefore, I know that this is, at least the improvement that I'm going to make. So before that, we knew that, we can't be too far away. And now, that, we can't be too far away if our gradient is small. This tells me that the progress that I'm going to make is at least as large as, that norm of that gradient squared times some constant. And now let's use strong convexity again. And there's a parenthesis missing here. Okay, so I can specifically apply that to x plus t g of x minus f of x star. So I'm just, subtracting f of x star from both sides, right? Now I go and actually plug in the expansion for the norm of the gradient squared, which we had on the previous slide. See, we had this is the norm of gradient squared is greater or equal than 2m times the difference, the distance from optimality in function values. Okay? So I take this number and I plug it in on this line. So I can express the right-hand side now entirely in terms of the distance to optimality. So as it, there's a bracket. They get f of x minus f of x star times 1 minus m over n. So what we have is that after one line search, if I was this far away from optimality before, now I'm this much closer. And so, of course, after k steps, well, it becomes this number raised to the k. If I solve and take logs and so on, I get this expression. And we actually use the fact that this tends to be usually a very small number, so log of 1 minus little m over big M is approximately m over capital M. But the equalities go the right way. So what it tells you is that it's essentially that condition number that determines things times the log of how far we are from optimality initially divided by my accuracy requirement. But the good thing is this really only enters logarithmically. So usually we'll have a good handle on this because we'll typically have a good lower bound on that. Often 0 is going to be the lower bound. And this is, you know, going to be maybe some relative accuracy of maybe 2, 3, 4 orders of magnitude. So it's a small number of steps. And this is very surprising, so always bear that very, very simple algorithm in mind when we look at more complicated ones. So let's actually look at a distributed implementation.
I just like in Spain.
What?
How you get log?
How you get them? Okay, let me derive that. So what I have is that f of, let's just give it a counter t, f of xt minus f of x star is less equal than f of xt minus 1 minus f of x star times 1 minus little m over capital M. Right?
Yeah.
Now, I can just iterate this inequality and get an f of x0 here and raise it to the power t.
Oh, I see.
Right?
Yeah, yeah.
Now I set that equal to epsilon.
Okay.
I take a log, so I get that ratio, original distance divided by epsilon. I take a log of this and we are done.
What are the small n?
Okay, so little m is the strong convexity constant. That's basically the flat parabola that we can sandwich between our tangent and the function value and the function. Remember, this was our function which does something. That's the tangent, and then basically, how much space there is to squeeze a parabola. That was our small convexity, our strong convexity constant. Capital M was the maximum curvature this function can take. Basically, how quickly it could actually kink up here entirely and go somewhere else. So it's basically that upper bound here. And if this gap is tiny, the problem is very close to being a quadratic problem, in which case I can converge reasonably rapidly. If this gap is large, I'll have to do a lot more looking.
Sorry, how do you compute those two?
How do I get that? That's very problem specific. And in some cases, for estimation, you may actually be able to play with that strong convexity constant a little bit. So this is going to be our regularization constant. But that's a little bit further. We'll get to that probably next week. Okay.
Excuse me.
Yes?
How do you know what is like x star is equal to?
You don't know that. But quite often you will have a lower bound. you might, for instance, know that it's non-negative. So if you know it exactly, it's great. In many cases, you will be able to compute a lower bound in certain ways. So probably next week, we're going to look at bundle methods. And in that case, we will actually see an explicit computational construction which iteratively gives me upper and lower bounds for the function that I'm trying to minimize at every step. And so I'm going to get tighter and tighter bounds. The advantage of this procedure being that I don't actually have to rely on theoretical convergence analysis, but can actually monitor the convergence of the algorithm as it runs. Which is highly desirable because in that case, my theoretical analysis may be bad. I may suck at theory, but at least I can run the algorithm and I can monitor at each step that it's good, and then I can just stop it as soon as it's really good, as opposed to when my bound is good. So in other words, I can trade off brains for computation. And that's always a good thing. So let's look at a distributed implementation. So here's the algorithm, right? It's exactly the one that we have before. Given a starting point, do the following thing. Compute the gradient, perform a line search, choose the step size via context of backtracking. So I didn't talk about backtracking. There's a lot more in Stephen Boyd's book. And then you update until we have converged. It's good enough. For instance, if the gradient is small enough. Now let's look at the various steps. The first part is we need to distribute the data over several machines in order to compute that gradient diffusion. Because basically our function is, that's the assumption I'm making, otherwise we have a huge issue, is going to be decomposable into a sum of individual function parts. Then I need to actually compute the gradients, partial gradients, and I need to aggregate. The next thing then I need to do is perform a line search. Now that line search means that I actually need to go forwards and backwards between a central machine and those individual machines to perform that stepwise analysis. And then in the end, I communicate back to some final machine, to get all the values, to update the new parameters and push them back. So let's have a look at what that means in practice. So here are our machines. And so on map, I go and compute the gradient on the subblock and emit it. Reduce, well, it just aggregates all the parts of the gradients, as you would expect. And then, I communicate those subblocks such that I know my search direction to all the machines. That's the first part. Second part, too. Now, I need to do the line search. And this is actually really costly because each step in the line search is a map-reduce iteration. Right? So I compute the function values and the derivatives at some point. I then ship this again through a reducer to one common machine. And then I decide centrally, based on what I've seen so far, where we're going to progress and what we're going to do with it. So in that case, it may actually be advantageous if I have this line search part. Let's say, here's the line search, and I know I should be checking this function value. But I could already do speculative evaluation here and here. Why would I do that? Because at each mapper, I'm going to go through the data once. This is the costly part. Forget about all the function evaluations. Touching the data is the costly part. So I get essentially, rather than just computing this value here, let's say we have 1 and 2 here, this is 0.3, I can already compute 4 and 5, possibly 6, 7, 8, and 9 for free, essentially with it. And then I'm not going to decide only, well, I'm here at 3, where should I have gone? I'm going to, now zoom in on a much tighter interval. So therefore, in one map-reduce pass, I don't only halve the interval, I don't only quarter it, but maybe break it down into eighths. So this way, I can cut down the number of map-reduce passes from, maybe 1,000 to maybe 3 or 4. And if MapReduce is the expensive part of your code, you win by a factor of 3 or 4 very easily. This is how you can do MapReduce by just speculative evaluation. But it's still expensive. So the question is actually, you know, can we do any better than that? You know, what's great is, you know, we have linear time, the number of instances. We have linear storage in the problem size, not the data. That's great. Log time and the accuracy, and you know, we scale perfectly while ignoring that pesky MapReduce part. But you know, we need that many passes for each of the line searches. MapReduce is actually horrible insofar as it loses state, because basically you have not even any guarantee that the same mapper is going to touch the same data again. We have a single master as a bottleneck. On top of that, it's going to be the slowest machine of all the mappers that is going to determine how slow your algorithm goes.